Hello, I'm Robert, and this time I'm fact-checking the false claim that we can't manage to extract enough minerals for the green revolution. So there's no doubt that it's quite a challenge, but it's one we can rise to. And the main issue is to extract the minerals in a way that is sustainable and that causes least disruption to biodiversity and the forests and so on where these resources are found. So first of all, one thing that is often not made clear is that we do have to increase production of minerals and fossil fuels and everything else. We've got the increasing population of the world, and then we've got the weaker economies rapidly industrializing in China and India and in Africa. So we can't get away from this. We do have to increase production of the minerals. And if we follow the fossil fuels path, we also have to increase production of fossil fuels, including coal and oil and gas. We will need far more of that if the entire world industrializes to the same level of industrialization as the EU and United States, Australia, places like that. So production has to increase on all paths. And people forget that if you are on the fossil fuel path, you do need minerals and so on for making the oil tankers, the oil wells, your cars, and so on. You need many more cars in the future, no matter what path we are on. Now, it is true that the renewable path does have a larger increase in the mining of minerals, but it has a much lower increase, it has a decrease in fact, in the fossil fuels. So now go and look at this, and these are the various paths. It doesn't include, if I go up and magnify it, see how it works, then it doesn't include the, I'll just move just a second. So, if you look at that, this is our current path before COP26, just from the pledges we have already. And this is the 2C path, which once we've got the Chinese and China's pledge and the United States pledge, the EU and so on, once it's all fully locked in, we'll likely be at that after the COP26. And then this is the well below 2C path. And if you look at it, if you look at the electricity sector, and on the path we're on now, without any additional pledges, gasoline is increasing. If you look at the transport sector, gasoline will also increase, and notice how the minerals are increasing, especially for transport. It's quite a big increase in minerals just on the path we're on already. On the 2C path, there's an actual reduction in gasoline by 2050, significant reduction, and there's a big increase in minerals. The total flux is less. And then if you look at the below 2 degrees C path, the total flux is between the two. There's a big decrease in gasoline, there's a big increase in minerals. So you might look at that and say, oh, we've got to move huge amounts of minerals around. But what this is about the mass flow. It's not the actual volume of the minerals. This is about everything, including the tailings for the mines, and removing the material that is above the mines, if it's open cast, for instance. And most of that mass flow of minerals for the green economy is only going to be moved a few hundred meters or a few kilometers, whereas the gasoline is often going to be moved thousands of miles. So it's actually, it can be much less impact, but we do have to minimize the effect. We've got to be very careful. We're moving so many tons of materials around the raw ore in order to extract the minerals. So we do have to be quite careful with the gas flow, with the mass flow. And there are many things we can do about that, including recycling the minerals. We need to be careful about about the mining, and this is what the World Bank calls the Climate Smart Mining Initiative, which is just being careful about how you do the mining. And these are global hotspots where we've got to be careful, especially where it's blue, that we don't have such problems. Where it's red, we do have them. And these are the different problems for different kinds of minerals. Anyway, I'm not going to look into that in detail just now. Let's go back and go back here. So this is Professor Harrington, and he gave this letter particularly for the United Kingdom. So it is UK focused, but it's a general problem. It's a general issue with. I can move back onto the screen. So it looks really quite difficult if you look at that. When you look at what the United Kingdom has to do, well, we've got a 20% increase in electricity to power the cars. That shouldn't be too surprising. Indeed, some people might be a little bit surprised it's as little as that. But we have a huge amount of electricity that we use for industry and for other things. And only a fifth of the electricity we use currently is needed to, if we move so that everything is, all the cars are electric, we add another 20% to that. The cobalt, if we use current batteries, we need huge amounts of cobalt. The United Kingdom, just for its own cars, needs the entire global cobalt production as it is at present for 2 years. We've got 1 year's worth of another metal, and we've got 9 months of lithium, and we need all current, that should be 3 months, all current copper production for 3 months. So, but we can increase, and that was the main point in this letter. He said we need new research and investment, and we can increase all this. One thing that you may get confused if you read the literature, you get people saying that we're going to use up all 90% of copper reserves in 40 years. This is not really true. What this misses out is that whenever we start running low on copper, then they go out finding new reserves, the vast amounts of copper in the world. And it's a case that since 1950 we had 40 years of copper reserves left. And we've still got 40 years left now. Indeed, it's increased. In the year 2000 we had 26 years worth. Now we're back up to 40 years again. So this, we have every reason to believe that in 1950 in 2050, just like in 1950, we will continue to have 40 years of copper reserves available. The big challenge at the moment is cobalt. And at least for our current generation of batteries, like for the next decade or so, we need lots of cobalt. It's to do with the cathode on the lithium-ion batteries. And the amount of cobalt they use is going down and down. So you can look at the big reduction. It used to be 28 in 2018. Expect gold to go down to 10 by the what's these units? I forget. I have to put that up. That's in kilograms of cobalt use for every 100 kilowatt hours of storage in the battery, and it's going to get down to 10 kilograms. It's still quite a lot if you think about it. 100 kilowatt hours. To store 100 kilowatt hours in your battery, you need 10 kilograms of cobalt, which is quite a lot if you think about it. So here's the idea of cobalt free or very low. That's not as low as it's going to get. That's for 2035. But sometime around then, we'd like to transition to new kinds of batteries that are even cobalt free or very little cobalt. Now, the problem with cobalt is that most of it comes from the Congo. And in the Congo, there are really not very good working conditions, and there's a lot of exploitation there, and people don't like the idea of funding what's going on in the Congo. And so that's one of the main issues with cobalt. And then another one is that there there are not that many cobalt, that much in the way of cobalt reserves known in the entire world, even including the Congo. And at the rate at which we're going through it, we're going to need 5 times as many by 2050 as we do now if we move to all cobalt batteries. And it starts to get a little bit tight. But then there are lots of things we can do about that. Reducing the cobalt, there's the also recycling it. And this is about how much cobalt we can recycle, and then the new sources. And for instance, in Europe, then it's quite a large. We have cobalt. We have mine tailings from old nickel mines. Cobalt is a byproduct of mining nickel and byproduct of mining copper. And if we mine lots and lots of copper and nickel, we get lots and lots of cobalt. But we only have so much requirements of those things. And so we can go through the old nickel mine tailings in Europe, and we can get cobalt from those. And we can also, there's a study has found quite a lot of cobalt in that we can actually find as decent resources to aim for, where your main aim is extracting the cobalt in Europe. Then we do have enough of it, but it's a question of whether we do it sustainably and in the right way of doing it, and that's the main issue here. Then, it's the same for all the elements, but I talk mainly about that one. So please don't feel we can't do it. And but there are things to be thought about doing it intelligently and carefully. And this looks like you've got graphite, lithium, and cobalt. It's 450%, nearly 5 times as much. The annual 2018 production we might need by then. And that's about silver. Now, I just want to talk about, so we can see we certainly have plenty through to the 2030s, and we can manage it with some pressure on our natural resources, but by recycling a lot. And the cobalt is actually needed for building the first generation of electric cars. So by the time we get, because we can recycle just about all of it if we have intelligent design of our electric batteries. So if it was just the cars we have already, then by 2030, by the 2050, we would be recycling just about all the cobalt. But we have to take account of that we are also rapidly industrializing, and lots of people will be wanting cars in Asia, in Africa, in India, in South America. They don't have them yet. And that is the main reason why we continue to have a big pressure on cobalt through to the second half of the century, if we were to continue using cobalt batteries. And so by if we can recycle just about all of it, if the number of cars in the world remain constant once we reach that point. So then there are alternatives for the future, that if we do end up still having to have cobalt batteries, I'm mainly focusing on that because it's one that people raise a lot, but we can do recycling with all the materials in our batteries. And we've got the new designs for batteries where you can take them apart easily. You can just dismantle the bit with cobalt is in, and you don't have to do much extracting at all. And so with carefully designed batteries, we can quickly recycle and easily recycle all the precious things in them. Now, however, there are alternatives for the 2030s, where, first of all, we do still need cobalt, and then certainly for other things as well, we have the manganese nodules on the seabed. And there used to be a huge amount of concern about that, but there has been a lot of work being put into mining it more responsibly. So these modules they're only in 4 places in the world. So we're not talking about digging up all the coastlines. Indeed, the biggest area here isn't any of the coastal areas. Indeed, none of them are really coastal areas of the sea, at the deep sea. And this is what one of the richest ones look like. Nevertheless, we don't want to mess up the ecosystem of the deep sea bed. And there are lots of snails and various other kinds of wildlife, and you get dolphins and things like so on in the shallower levels, and you get many sea creatures that live there on the seabed. And so when we mine the manganese modules, we want to do it responsibly, so as not to damage the seafloor, even the deep sea floor, or those in the middle of the seas, not so much coastal areas. And so there are many ways we can do it. First of all, the way the manganese modules formed is they settle out of the sea. Is the metals dissolved in seawater. Seawater is very rich in various metals. Indeed, we also get metals like that if we use desalination. So desalinating water is another way to get some of the metals that are in the seawater. But these have already been deposited in the bottom of the sea, and we can just mine them out of the sea, from the seabed. And so what we can do, so one of the main issues with mining them is the sediment. The sediment will then fall down to the seafloor, and things that can't move very easily, then they can get covered in sediment and then die. So to make sure that it doesn't harm those kind of creatures, so many creatures and other ones, these are like ploughs, and they're going across the seafloor, and sea snails and things, they can't get out of the way fast enough. So they're going to die as these things go over the seafloor, and in the various seaweedy things and so on. And I don't know what they have. I'm not actually sure of the details of what they slow-moving organisms, and they give examples there. Bottom-dwelling organisms. It wouldn't be seaweed that deep. And other marine animals and so on are disturbed by the noise. And the sediment gets churned up, so as it goes along it'll be killing some of the creatures, and then the sediment also could land on some of them and damage them. Now you can deal with the sediment by using these cowls that go over the ploughs, and that stops. And then you have other ones who use pipes that come down from the ships, and this avoids filling the sea with the sediment, which then settle down and cause problems. And the sediment from the ships, and it's mainly that they can get in the way of the algae near the surface. So if they use pipes to go down well below the surface, then this will fall down gradually to the surface, to the seafloor, and spread out, and it's not such a problem like that as well. And then for the inevitable life from the seabed that's going to be killed by the mining, of course you get things killed whenever you're doing mining. If you're just digging up the vegetation, if you're digging down and you're digging away the surface and so on. So you try and avoid harming as much as you can. And what they found is that that if you use strips along the seabed, then within about 7 years, then they can be recolonized. It looks very much like it was before, although some of the life that used to live on might take more like that, maybe like up to 25 years or something there. But looked at it again, they haven't done this experiment for long enough to know how long it takes for some organisms that need to firmly attach to solid foundations. And but they reckon that they can greatly minimize the impact of manganese nodule mining by doing it in strips, narrow strips, so they can be recolonized. They'd recolonize within 7 years, and then you go and mine the strips they colonized from, and you keep on doing like that. And so that way you always have you don't have, what you've got to avoid is mining large areas, clearing large areas miles across where there's nothing left anymore and there used to be sea life. So this is something they're looking at, and it's a big question, do we mine the seabed or don't we? And if we mine it, can we mine it sustainably? The important thing to realise it is just these four regions. It's mainly that one that we can mine, and the other ones too. That's one of the big ones. So it's not the entire seabed. Still, it's quite important. The manganese nodules are there throughout the seabed, but that's the only one where those are the only regions where they're very concentrated to the extent that they're worth mining. Now, another way that we can deal with this in the far future, I am especially interested in asteroid mining and in mining the moon. And this you might think, oh well, how can we possibly be mining asteroids? It's just so expensive to go into space. Well, the thing you need to bear in mind is the costs of space launch has gone down hugely. It started about 5,000 to 10,000, it's now dropped down to 2,500. It's $1,500 per kilogram with the Falcon Heavy. And NASA have the objective to bring that all the way down to hundreds of dollars. And SpaceX have plans that could lead them that way. There are other plans. There's the Skylon. I'm in the United Kingdom, and our Skylon is a way of flying into space in just one go, not like the space shuttle, but flying off from a runway. And it's been somewhat undermined, the economic incentive for it, because of SpaceX is so low cost, and it's a slightly different niche, and as far as I know it's still going ahead. There's also competition from China, which plans to do a space plane, and then India wants to do a space plane. And China has an interesting two-stage space plane, where there's one plane that flies up to quite a high altitude, and there's a second plane that's optimized for flying into space, which then takes off from the top of the fast-moving lower plane. Where Skylon does it all in one go, it changes from an air-breathing to a rocket to a different kind of engine. Once, basically a kind of rocket thing, once it gets high enough so it can't breathe in oxygen, getting enough oxygen. So there are all these ideas of getting into space, and by the 2030s, these may be down to $100 a kilogram, and it may keep on going down. At that price point, then space mining becomes really quite practical. The reason it's so practical is you've got some incredibly valuable elements in space, particularly platinum. And this is an example of one particular near-Earth asteroid called 1986 DA. It's 2.8 kilograms in kilometers in diameter, and so that's not that big, but it's one of the larger of the near-Earth objects. There's another one about that size as well, two of them, that were both known to be metal. They're basically made entirely of metal, a huge chunk of metal, 2.8 kilograms across, far wealthier than any mine on Earth. It's got vast amounts. This is a logarithmic scale. That's 1,000, 1 million, 10, 100, that's a billion. So the green are the world reserves, red are the amounts that there are. So look at the world reserves, that's about 100 million, and that's about, that's several tens of billions the amount of nickel in just one of the, no, is that nickel? No, that's iron. The amount of iron in just one of these asteroids is, it's more than 100 times the entire world reserves of iron. And the amount of nickel, it's a lot more than 10 times the amount of nickel we have by way of world reserves in just this one near-Earth asteroid. And you look at the cobalt, that again is many more than 10 times the total world reserves, 157 million tons. It's not that different though from the seabed mining, but how many is it there? Can I see it? No, sorry, that's the wrong one. Seabed. Oh yes. Now this is the seabed mining one. And we go down and look at cobalt. Yeah, it's only 44 million tons in that big, the one I pointed out, in that one there. 44 million tons. I think it might be over 100. Does it say here? 120 million tons in the seabed of cobalt. So now, if we go and look here, there's 157 million tons of cobalt in this just one near-Earth asteroid. So there are vast amounts of cobalt in space. Now, cobalt is rather low value, but it's worth returning it from the asteroid because it's got 90,000 tons of platinum. Got a lot of gold as well. And if you go and look at the prices here, the value, these are trillions of tons, trillions of dollars value. So it's got just short of 6 trillion tons value of rhodium, which is a very valuable metal that is mainly used for catalytic converters. But if we had so much of it, if we had those, where's the, it doesn't even list rhodium, but if we had this much, look at it, it's rhodium 1.25, that's 122,000 tons of, yes, 122,000 tons of rhodium in this one asteroid. That's a lot of it, a very precious, very valuable element, extremely resistant, corrosion resistance. It's sort of like platinum and better. And there's rubidium, there's palladium, iridium, platinum and gold, and vast amounts of all of those. And then we've got copper, cobalt, nickel and iron. And all of these, that's more than 10 trillion tons dollars worth of resources in this one asteroid. So when you're getting down to just a few $100s per kilogram launched into orbit, and you've got an asteroid up there that's worth 10 trillion tons, $10 trillion, then it begins to become economic to start sending up machines to mine it. Not necessarily astronauts, autonomous machines. They'll go up there. And lots of ingenious ways of doing it. If you've got a metal asteroid like that, there is a way, I don't talk into that here, there is a way of basically enclosing it in a big bag. And it's carbon monoxide you use, and you warm it up to a particular temperature. That causes the nickel and nickel and iron, I think, they turn into a gas. And then the other stuff falls out as kind of dregs. And then you can condense the metals off as well out of that gas in a kind of cycle into a kind of 3D printer. And you could actually attach a printer to this big gas bag in space. But you put boulders from the asteroid is likely made up of lots of metal boulders. So you could put boulders into these bags, and then you could have actually mining as well. And then the metal turns into a gas. And this is a system that's actually used for refining metals. And then you can condense the metals out of that gas, and one at a time, and then use them to actually print things with a 3D printer attached to your big bag. So you could actually even return printed things, 3D printed metal, back to Earth from your asteroid. Quite bad value to it. So there are lots of ideas the asteroid miners have come up with of ways that you could do it. That wouldn't mean not even digging. You just grab a boulder and put it into a big bag. You could put a bag around the entire asteroid if it was a small one. It's a little bit big for doing that. But there are lots of ingenious ways of mining these asteroids. Another ingenious thing is that these asteroids are generally they're spinning. Most asteroids are spinning at quite high speed. And what you can do is you can attach a tether So you may have heard of the idea of using a tether to go up into orbit from Earth. That needs very high-tech materials we don't have yet to actually just go up a lift into orbit. But if you don't need just an ordinary tether, just what's that stuff? The bulletproof material, Kevlar. You can make a cable made of Kevlar. That's very, very strong material used for asteroid tethers, for tethers in space. And if you were to attach that to an asteroid that is spinning around, then you can have a lift that goes up that tether, and it just goes out onto centrifugal force from the asteroid. It might have to power itself up a little way against asteroid gravity, and it would have to power itself a little way because the asteroid is held together by gravity, but not very far, and then the asteroid spins it away, and you get a free boost of all the way, and if you're lucky, your asteroid might be able to boost your payload all the way to Earth. Certainly a big reduction in the fuel from your asteroid by using this tether system. So you use the asteroid itself to kind of extract the metals. So there are lots of ingenious ideas that could greatly reduce the cost of asteroid mining. So it may seem incredibly impractical if you haven't looked into the details, but lots of very hard-headed people have looked at that, and the two mining companies have started up, and quite a lot of venture capital has actually gone into asteroid mining already. And they are doing prospecting, telescope prospecting, planning the first missions into space to go and prospect for asteroids and so on. And they're just getting their toe in the water. And actually Luxembourg is a bit of a key player in this. They are very interested in asteroid mining. This very small country of Luxembourg is a key player in asteroid mining, and they're trying to pioneer new laws for asteroid mining in Luxembourg. So it's something that I think we may well have by the 2030s, and if not the 2040s. I would be surprised if we don't have asteroid mining taking off in a big way before the 2040s myself, because everything has started coming together. We had several decades when the cost was so high to get into orbit. There's no wonder we didn't have much asteroid mining. We could have done it, but it would have been a huge, huge outlay in the 80s or 90s. It would have been a big risk. You would have had to risk tens of billions of dollars or something like that, or maybe even hundreds of billions of dollars in a new venture to do asteroid mining, and with a huge amount of risk because it had never been done before. But the costs are going very down, and it's the same with mining on the moon as well. Costs going into orbit, we may well get our first mining on the moon. Just as we have big metal asteroids, then there is good evidence of big deposits on the moon, on the rim of Aitken crater, which is the big crater in the south pole of the moon. And splashed out onto the rim, it seems to be the metallic core of the big impactor that made that crater billions and billions of years ago, splashed out onto the surface of the moon, and there's probably loads and loads of platinum there, iron, nickel, and all these things that we have there. We don't know the composition yet, but we've got lots of prospecting missions going to the moon. 2022 will be a big year for lunar robots. We're going to have lots and lots of robots, not just the Chinese ones, which we already had two already, lots of innovative ones, including we're going to start getting rovers exploring the caves on the moon, vast caves, and they may be as broad as kilometres across. It's only tens, maybe hundreds of metres across inside, and then the ice at the lunar poles and all the metals and so on. So, as you can tell, I'm very keen on space colonization, space settlement, but I think it's very important that it's done in a responsible way. And one way it can be done very responsibly is by seeing it as a way to offload some of the mineral extraction on Earth into space. So we don't need to go even mining these manganese beds that I told you about, these manganese nodules It might be we don't have to do that. It might be that by the 2030s we are off mining from asteroids, and asteroid mining actually might even cost less than mining from these mining space modules once we've got all the infrastructure in place to do it and got really low cost going into orbit. So I think it's possible. And by the 2030s we're getting our metals from space. I think that's a hard-headed possible thing to do. It's not fancy head in the clouds thinking. It's really hard-headed looking at the nuts and bolts of how you do it. And I've written my case for Moon First book, online book, goes into some of the details of that. So another thing that we may well have, but I don't talk so much there about asteroid mining. It's mainly about mining the moon. I talk about asteroid mining in, I think, my Touch Mars book might go into asteroid mining. I'm not sure. I think it might have a bit about that. Anyway, so the other thing to bear in mind, the innovations we're going to have, pretty certain we're going to have major innovations in batteries by the 2030s. Already talked about cobalt batteries without cobalt. There's a lot of research into air lithium batteries and lithium oxygen, sodium ion, and various lots of interesting ideas. Lithium air is a very exciting idea. It's got several breakthroughs still need to be made. But if we could get a lithium air battery, then its storage capacity is not far off gasoline. This means we could have batteries that give your car a huge amount of mileage, because electric cars have far more battery space than you have gasoline space in a petrol car, and the engine is relatively small and the battery is huge. But we could have planes flying off into space, not in space, because planes flying off to other countries. So right now we can expect in the early to mid 2020s, by 2025 there'll probably be lots of people flying around in electric planes. This is also already prototypes. They're being tested. There are people flying around short-haul flights for a few hundred. We can expect to be flying a few hundred miles. You'll be going across country, across the United States, and we'll be travelling in the United Kingdom from, say, Glasgow to London in an electric plane. We can expect that sort of thing by the mid-2020s. And again, these things might seem extraordinary, but if you've lived for the last several decades, like I have, anyone in their 60s, like me, has in their life there have been huge changes. I saw the advent of the personal computer. It happened in my lifetime. When I was a child at school, I saw the pocket calculator in my lifetime. When I was at school, we didn't have pocket calculators. We had slide rules at school. I did my maths using a slide rule at school, calculating logs and things. Using for multiplying, use it for log tables. We were opening up log tables and looking in the log tables. And in my maths department at school, when I did maths, we had a little clockwork machine for adding up. It was a calculator in the maths department. We didn't have computers in our maths department. Never, there were big computers in the 1970s. There were quite a lot. There's a fair number of big computers. When I was younger, 60s, they were very rare, but they were only in big. Maybe a university might have it. Maybe a big research department, a very big high-tech university might have a computer. When I was a child, one computer for the entire university. And in our maths department at school, we had our pride and joy as it were, was a mechanical calculator that you wound around. You put the sum into it, you wound it around, and you got an answer. That was my childhood. And when you went into shops, the shop, they didn't have automatic adding up of the sums. They didn't have little calculators. They added up by hand using handwriting. They just wrote out the numbers, or they did it in their head, or they just write down, £1, £1, 3 shillings and 5 pence, £2, 4 shillings and 6 pence, 3 shillings and 2 pence, 1 shilling and 11 pence. You'd add up all those numbers, and then you had the very eccentric system where you have 12 pennies to a shilling and 20 shillings to a pound, and they had to do all that by hand. So when I was a child and you went into a shop, sometimes you get out bits of paper and they'd be adding up these numbers in order to tell you how much you owed them. But others would just do it, the small items, they just do it in their head, and they add it up, and you just trusted them to get it right. Unless you're a mathematician, I'm not very good at quick calculation. So in my life, I've seen it change from that to what we have today. So that is only from mechanical calculators. That would be in 1960s. Now we're in the 2020s. So we're talking about 60 years. So what is going to happen in the next, say, 40 years? 30 years to 2050, that's half of that. And mobile phones and think of all the things, Skype, that was just it'd be absolutely incredible. But we also imagine things like flying cars, which haven't happened yet. So people were saying, in the future we'll have flying cars. That didn't happen. But we have had all sorts of amazing things. You look back at Star Trek, and they're imagining the far, far future, and they have the early series of Star Trek, the big clunky things that they put on their big clunky screens look very huge and clunky and chunky to us, and they don't have handheld. They when in like for instance Star Trek Next Generation, when they only have audio links to the surface of the planet, and you have to touch the communicator badge and you can talk via audio. They can't see anything visually, and they ask the away team to describe what they can see because they can't see it themselves. So you had Star Trek had the idea of spacecraft, and that's the Next Generation's Star Trek, had the idea of spacecraft travelling around faster than light, containing antimatter, containing dilithium, whatever that's supposed to be, space warp and so on, matter transporter, which is absolutely, probably never happened in this universe. It seems very impractical. They had all that, and yet they weren't able to manage video signals from the away team. And even within the Starship Enterprise, they didn't have video signals from, say, engineering, except if you go and talk to a video screen in the wall. So they actually had the idea, video screen in the wall had to be connected to another video somehow physically connected by wires or something, presumably, because they couldn't just talk. And yet they had these holographic doctor or holographic 3D holographic things. So that gives an idea of what back then, that's not that long ago, we were thinking about what the future would be like. We just didn't imagine Skype. We just didn't imagine mobile devices in your pocket that had video, that could let you talk by video to someone on the other side of the world. We didn't even imagine that you could have video like that and talk to someone 2 rooms away, the other side, in another part of the same starship. So people, you just get used to what you have around you. Indeed, some of you listening to this may have actually lived through what I lived through, and you just forget it. You just come to everything you have now, just seems normal and natural, and you just forget what it was like back then. That we just didn't see how this was possible. So that is why I think that really the most important thing is to make sure that we are doing something that will work through to the year 2100, so we know it's feasible. And then we plan it out in detail for the next 10 years in a fair amount of detail for the next 20 years. Beyond that, it's all right to be sketchy. Just that you've got a vague idea. You have enough worked out to know you can do it with current technology. You can be pretty sure when the time comes, you will have other ways of doing it. Especially 20 years ahead, 30 years ahead. Any time after 2050, I don't think we can really realistically foresee exactly how we are going to do it. As long as there is a way to do it, that's all that matters. So I think it's quite feasible that we do have these lithium air batteries. They are it's not necessarily that, it might be something else, but they are only a few steps away. They're not really that far away, especially when you look at it's nothing like the transition from, say, a slide rule to a pocket calculator, which only happened in a lesser time scale than that. So that was from sometime in the 60s to the 70s. I think you go from slide rules to pocket calculators. I'd have to look that number up, look up the details. So I'm rather riffing. I sometimes go a little bit off topic. Anyway, this is my long video. I'll be doing a short video afterwards. So anyway, we can expect lots of developments, and these are just some of the ideas. They're not necessarily what's actually going to happen, but we can certainly expect battery breakthroughs, and I will be very surprised if we don't have batteries with hugely more capacity than we have today, if not necessarily quite as much as lithium air, which is roughly the same capacity as gasoline. If we achieve lithium air, then say we achieve lithium air by 2035, then in the late 2030s we can expect to have intercontinental travel in planes that are battery driven, because they will have the same energy density as gasoline, jet planes driven by batteries. We can expect that we may have that in the 2030s. We may also have planes flying into space, flying to the moon, so it's not at all impossible that we have planes flying to the moon in the 2030s or 2040s. And then if we are at that level, of course not flying, they turn into rockets once they leave Earth, but travelling to the moon for a week, 1 week holiday on the moon, may be commonplace by the 2040s. So in that sort of a future, I think we may well be mining metals from space. Whether or not, I think the main thing is that make sure that we are as sustainable as possible. The most important thing right now is to not damage the ecosystems, the climate-friendly mining, and look forward ahead and know that we can get all the metals we need. We don't need to plan everything out, and be careful. We don't really need to start the manganese modules yet. We can continue to research into that in case we need it, and the main thing is just to do the climate smart mining for the next couple of decades, and then I am sure, well, we already know that we can do it. The main question is if we can do it in a climate friendly, in a how biodiversity friendly, how in terms of equity and so on. And I am sure we'll find much better solutions than anything we can think of now, once we know what technology we have in the late 2030s, 2040s. Trying to do that now is a bit like someone in the 1980s trying to design how we should do it today. It's just too long ago for them to be able to work out in any detail. Indeed, even in 10 years ago, it'd be very hard to work out in detail what we do today, because the cost of renewables has fallen tenfold, and that could not be reliably predicted. There were people who hoped for it, and sometimes they claim to be profits because they said, oh, it's going to reduce tenfold, but nobody knew in 2010 that renewables would be reduced tenfold by 2020. It depended on advances that hadn't happened yet, and there was no way to actually know it. You could be optimistic about it, you couldn't know it. Just like we thought that we were going to have flying cars today, and we don't. So we do have the flying drones. Maybe sometime in the near future we have flying drones with people on them. We don't yet. And we didn't predict drones. Again, not really. There's some very fanciful ideas that look like them, or maybe in a way we predicted drones. Perhaps that is a little bit more. Maybe we predicted drones, but we didn't predict video. It's a bit how far back you didn't predict Skype. It's just. I think there were science fiction stories that sort of predicted drones, but not really. Not. Anyway, I'm just rambling on now. I finished this video. I think I've said everything I want to say. Let's have a quick look. Anything I've left out? Okay, so I'll upload this. Let's see if there's anything else. I may do a shorter version of this since I'm farther on, but some of you may be interested in what I'm saying here. So here goes. I'll upload it.